Thank you very much, Ilaria, and thank you everyone for joining me for this webinar today. I would like to share my screen, and in the meantime, I would like to thank you, Ilaria, BiRex, and there for the possibility to have this event. Let me, please tell me if you can see my screen in full screen presentation.
Yes, I confirm.
Okay, great. So today in this webinar, we are going to explore together how AME, additively manufactured electronics from Nano Dimension, is reshaping the way we can imagine, we can design, and finally manufacture electronics and electromechanical structure. This is really disrupting the field of rapid prototyping, and we will see together how. This is the agenda. I will start with introducing Nano Dimension as a group. Then we will talk about AME technology. We will see how rapid prototyping can leverage AME, especially for the development of medical devices. I will show you some real applications from some of our customers. If there is time at the end, I will show you a video about, it's a demonstration, virtual demonstration. It's a video about demonstrating how the machine works. And finally, we will leave some time for Q&As. Who is Nano Dimension? Nano Dimension today is a group of companies, or if you prefer, is a company with several divisions, which basically represents a leader in the field of digital manufacturing. We started approximately 10 years ago with a big vision and a great idea, which is to apply the additive manufacturing concept to a new field, which was the electronics. This is represented here on top left with the Dragonfly 4 AME machine. And then over the years, the company grew a lot dramatically. And recently, we acquired other two quite important and big groups, Desktop Metal and Markforged, which are now 100% part of Nano Dimension and represents key pillars of our strategy in offering additive and digital manufacturing solutions. You can see here other branches and divisions of the company. We develop materials in-house, we develop the software in-house, and we also, one of our key products is also SMT, so surface mount equipment. It's a company in Switzerland called SMTech, which provides machines for pick and place, dispensing, oven, everything needed for surface mount of electronics components. Here is a quick overview about the technologies we are offering today together with Markforged and Desktop Metal, which includes binder jetting, Desktop Metal, basically DLP through EnvisionTech, parts of Desktop Metal, additive inkjet, of course, the Dragonfly 4 and the additively manufactured electronics, and also FFF, which is a key technology of Markforged. Here is a snapshot of different technologies we can offer, different materials, ceramics, composites, electronics, metal, metal casting, and polymer parts materials are supported by our portfolio. So it's quite a comprehensive portfolio of solutions for different needs. Here you can see some of the parts built and manufactured with Desktop Metal, and top left, Markforged. Top right, you can see polymer parts made with DLP technology, so basically EnvisionTech, and other parts made of silicon carbide, electronics, of course, composites from Markforged, continuous fiber reinforcement, FFF technology from Markforged, copper, stainless steel, metal, and so on. But let's focus on the main topic today, which is AME, additively manufactured electronics. There was no AME before Nano Dimension. So this acronym has been invented by Nano Dimension to make it different compared to the 3D printed electronics, which may look the same, but it's fundamentally different because most of 3D printing technology offers features which include printing conductive material, conductive traces on existing substrates or structures. With AME, additively manufactured electronics is a really additive process which includes building the whole structure from scratch, including the insulating, the dielectric, and the metal structure. So the technology is based on inkjet. So everything starts from two inks that we developed. A dielectric ink, which is basically an acrylic monomer that is cured using UV light, and a conductive ink based on nanoparticle of silver, which is sintered using infrared radiation. Short video to explain the process. So the machine includes two tanks with the two materials, dielectric and conductive inks, which are jetted using two industrial printheads with 512 nozzles each. So basically we are jetting droplets of the two inks of 36 micron diameter. We jet the conductive and we sinter using infrared radiation. Then we jet the dielectric and we cure using UV light. This process is done layer by layer, and the whole electronics or electromechanical structure is entirely built in a fully additive way from scratch. It's not printed or jetted on existing substrates or surfaces. How does it work a little bit more in detail? So the machine supports digital files such as Gerber, ODB++, STL files coming from different tools, from ECADs, for instance, like Altium or Allegro, where you can export Gerbers or ODB++, but also files coming from the MCAD world, so from mechanical tools like Fusion 360 or SolidWorks, for instance, where you can export STL files. But also the machine supports file coming from another world, which is the world of electromagnetic simulation tools, such as CST, for instance, or ANSYS HFSS, where you can still export STL files fully supported from the machine. The machine has integrated a slicer, so starting from the design of the 3D object, the machine slices the design in layers of 1.25 micron of thickness, and each layer, it's very simple. For the machine, it's basically a matrix of pixels, it's an image, and each pixel is a droplet of conductive or dielectric ink that it's jetted. As I said, we are printing the droplets through two industrial printheads with 512 nozzles, and each nozzle, each droplet, is approximately 36 micron of diameter. And so this is basically the pixel size of this matrix of pixels. This is more or less the simplified explanation of the process. The real process is a bit more complex, but this is enough to explain at least the principle. As I said, it's a fully 3D additive process, which means we have completely freedom from a form shape point of view, which means we can really create 3D objects and multi-layer structures, such as, for instance, multi-layer, high layer count multi-layer PCB, like 30, 40, 50, even more layers PCB in 1 or 2 millimeter boards, without the need of having vials, drilling, electroplating anymore, because we can easily print vertical or diagonal connections, as you can see, for instance, in this coupon here in the middle, where you can see a diagonal trace going through a ground plane, connecting, for instance, two different levels of the same 3D structure, or two different layers if you want. We can create 3D dielectric structures, as you can see here, like dielectric lenses, very useful for antenna applications, for instance, dielectric pillars, but also cavities and 3D conductive objects, like 3D coils, twisted pairs, and also coaxial cables. As you can see here in the middle of the test coupon, this is a fully 3D printed coaxial cable that can go in any direction in 3D. Here it's just a flat coupon, but the coaxial cable and also the twist pair and the coils can go in every direction in 3D that you want. We can also print dielectric structure for weight reduction, such as honeycomb structures or any other shape that you may have in mind. We can print also bus structures for parallel communication, and we can even print passive components like multi-layer capacitors and inductors. Here is an example of what we can print. We mentioned already printed coaxial lines, but here you can see in the X-ray image on top left a 3D example of a coaxial line, 3D traces, diagonal, vertical traces to connect different level of the 3D electromechanical structure or different layer of a multi-layer PCB, dielectric lenses for antenna, ground plane and ground mesh coils, inductors, twisted pair capacitors, shielding structures, waveguides, and whatever you can think of. Regarding the conductive material, thanks to the additional degree of freedom that our technology offers, you can use it basically, of course, for the normal use, which is as an electrical conductor. But you can also use the silver ink, so the conductive ink, to print thermal management structures, such as, for instance, thermal coins, thermal vias, and also completely 3D printed heat sinks. And the third use, which is to print shielding structure. So imagine you have a via fence. You can replace the via fence with a 3D printed shielding wall, for instance. And you can do even more, because we can print flexible structures as well. On the bottom right image, you see a flex rigid structure. And this is due to the fact that when printed very thin, I mean something like 280, 300 microns, our dielectric itself is flexible. So this is not printed on a flexible Kapton substrates. It's entirely 3D printed on our machine. And we can print hybrid structure, flex rigid, like in this case. And we can also print multi-layer flex, much more complex structures. But we can also achieve flexibility playing with the geometry using the additional degree of freedom that AME offers. In this case, in the video, indeed, you can see that the flexibility is achieved using this type of geometry, like a mesh that allows a certain degree of flexibility without the need of printing very thin. Our technology is also used, this is a very popular application in the last couple of years, for packaging and to build a system in package with embedded active or passive components, discrete components, or even bare dies without the need of wire bonding. We will talk a little bit more in detail in the coming slides. By the way, I anticipate the way we do that is that we jet. For instance, for bare dies, we jet the conductive ink directly on top of the beds of the die without the need to do the wire bonding. So to summarize, the benefits of AME technology, of course, it enables fast prototyping, shortens significantly the time to market, and reducing in parallel the R&D costs. You can iterate very fast. With one iteration, you can test multiple design and choose the best, the design which works best for your application, reducing a lot time and cost, which means in the end developing a significant competitive advantage. But it's not just time and cost; it's also about the value of your solution, because with AME you can go beyond the limitation and the constraints of conventional technology, adding value to your solution. Also, AME is enabling the so-called digital inventory and cloud manufacturing that basically allows the production to manufacture the parts on site and on demand, including production, for instance, of spare parts without tooling costs, eliminating the need to make big stocks and free up financial capital in the end, changing completely the paradigm of electronic manufacturing. Last but not least, sustainability. It's a completely additive process. No waste, no harmful chemicals are involved in the process. Everything can be done in-house, which also means retention of sensitive intellectual properties, because you don't need to give your strategic design outside for manufacturing. And it's a one-step process, which means it's very efficient and from energy point of view, which means in the end low CO2 emissions, so carbon footprint significant reduction. And this is an example of how our technology allows sustainability compared with, for instance, traditional PCB manufacturing in this case. As you know, to manufacture a multi-layer PCB involves a lot of steps usually, and a lot of machines that consume a lot of use a lot of energy, and energy is directly translated into CO2 emissions. With our process, and these numbers are not coming from Nano Dimension, is a third party in the UK that made this analysis. Our technology allows 94% CO2 emission, so a lot of energy consumption is reduced. We don't use water at all. 82% use of chemicals, and we do not use harmful chemicals at all. All the chemicals we use is basically ethanol to clean the print heads to avoid clogging. And there is virtually no waste. You see here 99% instead of 100% reduction, because 1%, but actually with the latest upgrades of the system is even less, because we have now improved our recycling system. So we even recycle the conductive ink after cleaning the print heads. This is all the waste that is produced by this system. Only the dielectric, basically, because this DCI is recycled, only the dielectric that comes from after the process of cleaning the heads of the machine. And this is a slide according to DHL, just to explain the power of local manufacturing and digital inventory. A similar type of approach, according to DHL, may cut trade and transportation by 40%. So you can imagine the advantage from environmental and sustainability point of view. This is a very popular question that usually my customers, before becoming my customers, they ask. It's a fair question, actually, because we are talking about a capital equipment investment. It's an expensive machine. It's an expensive equipment, which has required many years of development and investments from Nano Dimension of hundreds millions of US dollars. So yes, it's a capital equipment investment, and also involves somehow leaving your comfort zone, because most of the customers I talk to, they feel comfortable working with processes which are well established. They know very well. So starting something new sometimes means leaving your comfort zone. But in the end, this is, in my opinion, a necessary step for innovation. Since this is a medical webinar, I want to mention a statement from Einstein that he said that insanity is doing the same things over and over again, expecting different results. So this I think represents well how innovation may require leaving your comfort zone. The answers that AME and Nano Dimension and I can give is that why now? Because now the technology is mature. Dragonfly 4 is called the Dragonfly 4 because it represents already the 4th generation of our machine. Nano Dimension over a few years launched several generations of the machine and went through accelerating more and more the development of this technology. This machine is now available since end of 2021, early 2022. And we have not a 5th generation of this machine in our near roadmap in the next few years. And there is a reason behind it. It's because we achieved a reliable machine, reliable process, repeatability, and a very good repeatability of the process and of the results, a very good yield. So now most of our investments are not going towards launching a new generation of the machine, but it's going in the direction of developing new materials for specific applications. Another reason is simply because AME allows a next degree of innovation. Means going beyond the current limitation of conventional technologies. And also, last but not least, AME adoption, it's a process that takes time. As we said, it means leaving your comfort zone, developing knowledge about new process, how to design, what you can do, what are the limitations as well. But you have to take into account that many companies already started to develop knowledge on this technology. We have now almost 80. This is a little bit old, this slide, but I think we are now close to 80 systems installed globally. So sometimes what I ask is, okay, it's fair that you ask yourself if you can afford the investment, but don't forget to ask yourself if you can afford not to invest in this technology and lose competitive advantage towards your competitor. Let's now dive into the real topic of this webinar. Now that we know a little bit better how the technology works, we can better understand the advantages and the use case when it comes to medical application. Of course, when we are talking about medical device development, it's clear that there is a rising demand for innovative devices, which is driven by the population aging, the new disease, pandemic, and so on that we have seen in the last few years. There is a shift of the paradigm towards personalized, patient-centric treatments, and then rising needs for fast development and fast prototyping of highly customized solution for the patient. On the other hand, we have to take into account the typical medical device development phases and the time that each of the phases usually require. Of course, it depends on the complexity of what you are trying to design. Could be maybe a bit less in some simple cases, could be more in more complex devices, but this is more or less the timeline going from concept to the launch of the device. Of course, where AME can help a lot are the two first phases, the proof of concept and the prototyping, where we can actually reduce the time from months to weeks, or for more complex projects from years sometimes to few months. But it's not just about time, again, it's also about cost. Because while reducing the time, AME also allows a dramatic reduction of the costs for each and every single iteration and for the whole development projects as well. Third point is the value. Because, okay, we reduce the time, we reduce the cost, but in the meantime, we also increase the value of our solution because we can go beyond the limitation of the conventional technology and create solutions with higher value. And this is what we already just said. AME enables design and production of highly customized, patient-centric, multifunctional electronics and electromechanical systems, also with embedded discrete, passive, active, or even bird eyes, so with a lot of different components. Of course, this also allows miniaturization together with customization and integration of different functions in the same device. So fast prototyping, possible simultaneous validation of multiple design in one iteration, which means agile iteration in the end, and cost reduction, reducing finally dramatically the time to market. So we reduce, as we said, time, cost, but we increase in the meantime the value of the solution. Let's now dive into real examples. I will start with CELTRO. CELTRO is a company that identified this need. The need, it's medical implants, basically, which rely on batteries, first of all, which is the first problem. It's the first problem because batteries, first of all, they are big, then they run out of power, and sometimes they fail. And this requires surgery because even if they don't fail, from time to time they run out of power, and so you have to replace, and you need to go through surgery. Also, the leads represents a big problem in medical field because leads break, leads corrode, And so this is another problem that they identified. So they started with a first product, which is a pacemaker. The idea, starting from the yesterday solution, which is actually also still used, pacemaker is implanted underneath the shoulder, and there is a lead going through the vein to the heart. The device is quite big as a battery, and so from time to time needs replacement. The second generation, it's implanted. It's a catheter implanted solution, but still as a battery, which represents approximately half of the size of this device you see here in the middle of the slide. So the solution from CELTRO is, imagine they still want to be catheter implanted solution. So the pacemaker goes from the femoral vein through the catheter, is pushed to the heart. But the idea is to make the device much smaller because you remove the battery. Since you remove the battery, it's no longer it's implanted for life. Basically, it does not need replacement. And the idea is to harvest the energy from the human body, and we will see how. So from the literature, energy harvesting can come from environmental energy like solar, infrared, or wireless energy transfer, or can come from human body, like kinetic energy, for instance, which can be piezoelectric based, for instance, thermal energy. But CELTRO wants to use, idea is to use a different type of energy, which is electrical energy coming from the human body, from human cells themselves. The principle is that every cell in the human body, it's an individual battery in the end. Between the inside and outside of the cell, there is a voltage, and there is a swing of approximately 100 millivolt each and every cardiac cycle. Of course, it's not possible to access the inside of the cell because the cell either die or rejects. But what they can do, we can do, is we can access the intracellular and still catch some of the electrochemical potential from the cell. Of course, one cell is not enough. We are talking about nanowatt electronics for this type of pacemaking systems. So what they need to do is to have an array of electrodes, and you can see here in the slide that there are several needles. Each needle is for an individual cell. So if you have enough needles, you can harvest enough energy for pacemaking activity. And this represents an implant for life, much smaller than conventional pacemakers. Don't need replacement, and it's much less invasive, of course, because it's much smaller. And also the cost to produce such structure is much lower, which means we can have a broader market and widen geographic penetration also in countries which has lower budgets. So the idea, we started to work with them, and the first phase of the project is to, of course, first of all, to manufacture the needle, and then to install the needle in a plastic 3D printed structure. And this was the phase one. Phase two is where we worked together with CELTRO using AME technology. So basically, we are printing dielectric ink to create the structure and to have a reliable mechanical structure of the needles. And then we print conductive ink to connect the electrodes of the array of the needle. The main question was from CELTRO was, can you do that? Is this good technology good enough? After testing, we found out that we can do that, and the technology is good enough. We completed phase two. Phase three is ongoing, and phase four will require, of course, the full qualification of the process. So between phase 2, which is the proof of concept, and phase 3, the main difference is to go from proof of concept with only 16 needles to a higher number of needles to harvest the energy that is really the energy they need for pacemaking application. This is the structure that we built, and especially on the right picture, you can see the needles sticking out of the dielectric structures. And from the image in the center, you see the connection between each and every needle, each and every element of the array of electrodes, which is made using the conductive ink. And of course, the same principle can be applied not only for pacemaking, but once it's approved, the same principle will be used or can be used for different applications like incontinence, hypertension, sleep apnea, and so on, opening an entire market for this type of batteryless implants. The second example is from the University of Alberta, and it's regarding monitoring of effectiveness of brace treatment for scoliosis. Basically, brace treatment has been proved as the most effective way to treat the scoliosis, non-surgically speaking. The goal is to, in the past, it was mainly to stop the curve progression, but nowadays is even to correct the spinal curve if you wear the brace for enough time and if you wear the brace properly. So the problem here is to monitor how much time basically the brace is wear from the patient and how well they wear the brace. This was done in the past using typically data loggers wired at the beginning. Then starting from 2010, 2008, 2010, also wireless connection came. Alberta University developed in 2017 a Bluetooth low energy brace monitoring systems, which was one of the first which could be, due to the smaller dimension and lower power, could be embedded, allowed to be embedded directly on the brace and with wireless connection connected to a PC. So the device included the data logger, temperature sensor, force sensors, everything embedded directly in the brace. But the point here, again, the demand was to, can you make it smaller and can you also reduce the power? And the objective, the answer is yes. So Alberta University, they made a next generation version of the sensor based on semiconductor MEMS. This was one of the first examples of a 3D stress, strain, and shear forces sensors. And thanks to this technology with smaller dimension and lower power, they were able to install in the same brace multiple sensors to have a better understanding of the biomechanical behavior of the brace. The limitation here was the PCB, by the way, which was really limiting the sensitivity due to the thickness, was limiting the sensitivity of the device. So the idea was to use AME and Dragonfly 4 machine to make a new version with a much thinner PCB, which can improve the sensitivity quite a lot. This was just the first attempt, and sensitivity was improved approximately 30%. They are now going through optimization of this sensor, of this design, because changing the thickness of the board and maybe changing also the profile of the board, you can most likely even optimize further optimize the sensitivity. Another application from Technical University of Liberec in Czech Republic. This is a bioreactor for cell cultivation. It is well known in the literature that electrical stimulation can enhance cell proliferation in the cell cultivation field. So the idea here is to place scaffold on the bottom of the PCB bioreactor. Well, in this case, the conventional technology was based on glass, was not a PCB. Scaffold on the bottom, they see the cells on top of the scaffold, and they apply electric fields to enhance the cell proliferation. And they then monitor how the cells behaves. The problem of this conventional structure was that the conventional method was quite complex, time-consuming, and expensive, requires chemical etching and a complex assembly process. So the solution with AME was the PCB bioreactor, a fully 3D printed structures that includes the electrodes, the traces to apply the electromagnetic fields, and the bioreactor structures as well. Our materials, of course, have been tested for biocompatibility and cyto non-toxicity, which is mandatory for this type of applications, and it was very successful in the end. It's a one-step printing process, which means it's very fast and very cheap. This is the principle. So as I said, the nanofibrous scaffold are placed on the bottom of the bioreactor. Cells, they seed the cells on top of the scaffold, they apply electric fields, and they monitor the cell behavior. So the benefits of using the technology is of course as I said, the biocompatibility, which has been proved of the conductive and dielectric ink. So the PCB bioreactor has been proved to be safe and appropriate for cell cultivation. Of course, they can work, the additional developments of these structures can include to design a different shape for the traces, to apply different electric stimulation parameters like different electric fields, different voltage, different frequency, or they can change in vitro parameters such as the cell density, cell type, and so on. And they did it actually. This is a next generation, an evolution of the first PCB bioreactor project. And as you can see in this case, they built and printed an array of bioreactors, because the idea behind this principle is to compare the results from the different bioreactors, applying different signals, so different electric fields to each and every bioreactor, or different cells with the same stimulation, for instance. So you have full flexibility. You can have also a bigger array, use different parameters, change the electric fields you apply, or change the cells, and see the results and compare the results very easily. Second example from Technical University of Liberec. It's a planar sensor for low frequency electromagnetic fields. This is also related somehow to pacemaking, because the pacemakers are, of course, shielded, also the wires, but the electrodes usually are not. So there is a need to monitor electromagnetic fields around the human body. And this can be done with this sensor, which has the same shape and dimension, very similar to the ECG electrodes, as you can see here. So the design is based on 3D spiral coil in 10 layers, with serial connections, and the overall dimension corresponds more or less to the size of the self-adhesive ECG electrode. So it's very easy to use, is completely without the need of using and embed ferromagnetic materials inside the device. So it's a one-step fully 3D printed sensor. And after measuring the device, frequency range from 100 Hz to 100 kHz, Technical University of Liberec found a very good match with ANSYS HFSS model. So the main advantages which are directly linked to AME technologies is the possibility to have very small planar sensor without any type of external ferromagnetics cores embedded in the device, but it's just a spiral coil entirely 3D printed, which allows a high winding density comparing with to conventional winding technologies or manual winding methods. Of course, additional developments in the future includes, for instance, 3D imaging using multiple sensors of this type to have 3D imaging of electromagnetic fields to determine the effects on living organisms. As I said, the materials have been proved already to be biocompatible, so everything has been validated already for clinical research and applications on the human body. Example number 3 from Technical University of Liberec. This is a printed, fully 3D printed flux gauge sensor. This type of sensor have a lot of different applications in the medical fields, which includes the monitoring of magnetic fields produced from the human body, from the heart, for instance, or detecting ferromagnetic materials in the lungs, and also supporting magnetic resonance imaging equipment calibration. The manufacturing idea is quite complex, actually, because it involves different parts assembled together. The design and the principle is based on a metallic ring of Vitrokov, which is a ferromagnetic material, which have to be embedded in the structure, and everything must be aligned. So the process is not easy, it's time-consuming and expensive. So the idea was to use AME technology to encapsulate the ring of Vitrokov that you can see in this slide in a cavity, 3D printed cavity in using a Dragonfly machine, and encapsulating, continue printing on top to encapsulate everything. So you can see here the schematic of the design. This is a portion of the sensor where you can see that the ring of Vitrokov is encapsulated in a cavity, and all around the Vitrokov core there are coils 3D printed with AME. And this is the final result. You can see from especially from the image on the right, that there is the metallic ring of Vitrokov material fully encapsulated in the dielectric, and with the metallic, with the silver coils going all around the ring of Vitrokov material. This was an improvement of the same device using the same principle, but with enhanced sensitivity, thanks to the different shape of the Vitrokov ring. In this case, it was not a ring anymore. It was called racetrack due to the shape of the material, and also improving the design of the coils all around the Vitrokov material. Another example from IIT, the Italian Institute of Technology. They developed a bidirectional optoacoustic brain interface. So the idea was to stimulate the brain through a needle, basically, stimulate the brain with light, with an optical emitter, and with a receiver, ultrasound receiver, acquire the neuron's acoustic response. Both the devices, the idea was to integrate both the devices in a single element. So having in the end both the optical emitter and the ultrasound receiver embedded in the same device. This is how the needle, the tapered neural optical fiber interface works. It can be used both for actuation, which means to control the brain function, and both for sensing, so to read the brain activity. For actuation, IIT can control the brain functions using optical signals, so an optical fiber that is encapsulated in the needle, temperature, or they can control the brain function through drug delivery. On the other hand, they can sense, again, using the optical channel, optical fiber, or monitoring electrical signal using the electrodes that, as you can see here, is placed very close to the optical window, or through chemical response of the brain, of the same region of the brain. As you can see here, there is on the needle an optical window. Underneath, there is an optical fiber, and each and every optical window goes in a specific region of the brain to stimulate a specific region of the brain, cerebral L5, L6, cerebral cortex, or hippocampal region, and so on. Very close to the optical window, they placed the electrode, which can monitor then, after stimulating with light, can monitor the response of the same region, brain region. As you can see, this is a highly non-planar structure. So the main challenge for them was to interface this structure with the rest of the world, with the rest of the system. First of all, there is an optical channel for light delivery and collection. So there is an optical fiber and a ferrule for light injection or collection. And also there are the electrodes. So there are also the electrical interface that must be somehow connected with the outside world. So using AME, they were able to make a package for this highly non-planar and complex structure. As you can see from the image here on the top, they built a 3D PCB with a cavity where they put the optical fiber and the recess for the ferrule, which is used for light injection. Also on the same package, there are the connection pads and the connecting structure to the electrodes, and that brings the signal from the electrodes of the needle to the soldering pads of the package, which allows then interface with the external system. The way they did it is that it's not a single step process in this case. So they had IIT had to engineer a process to make this complex package. And the way they did it is that they, as you can see from the top view on the top right of this slide, they built a stencil so that they could remove, after printing the base part of the package with the recess, to put the fiber, the optical fiber, they can use the stencil to put the structure back and continue to print on top. So basically, the first step is to print the first part, as you can see here, with a cavity. They stop the printing process. They take the first part of the package. They connect physically the optical fiber in the recess and the ferrule. They put all the structure back in the machine using the stencil. So it's a self-aligning process, which is good enough for this type of application. And they continue to print on top. So they start to print on top of the needle, of the electrodes of the needle, the electrical connections, and then finally they encapsulate everything in the dielectric to isolate and also to provide additional mechanical stability. Thanks to the flexibility of the technology, they were able and they are able to easily customize the system, to have, for instance, a single electrode instead of 2 electrodes, or to have a four electrodes PCB instead of 2, as you can see from the picture on the right here. Second example from IIT. This is the second part of the system, basically. So we said that first part was to stimulate the brain with the light, with the needle, and then collect the electroacoustics, the ultrasonic response of the neurons using the ultrasound receiver. So they developed for these applications, but also for the same principle and same device can be applied for other applications such as ultrasonic medical imaging, blood flow measurement, or photoacoustic imaging as well. So for all these applications, IIT developed a silicon die. The design is based on an array of electrodes, but again, it's a complex structure, and the challenge, once again, is to package this die and interface the device with the external world. And once again, they used nano dimension AME technology, Dragonfly 4 machine, which allowed them to package the device without the use of wire bonding for connections. And the way they did that is that they printed the first part of the project, of the package, including a cavity and a self-aligning structure with also a base connector design, which can be easily customized for different type of external systems. In the cavity, they put the die, and then they continue to print on top of the die with dielectric to encapsulate the structure, and conductive ink to do the connections, replacing basically the wire bonding, jetting conductive ink on top of the pads of the die. You can see here the first step, so the housing with the cavity and the customizable connector. The second part is the silicon die placement, and the step number 3, which is printing, encapsulating everything, and printing the tracks that connects the pads of the die with the connector. And this is the final results. From mechanical point of view, and also from electrical point of view, the solution has been tested and has been proved to be good enough. This was my last slide regarding the applications. Thank you very much.